my name, and I put my GitHub and also my email there. So if you have any question regarding this slide, regarding this talk, just drop me a message. I have nothing to declare, and the only information for you is this is a GitHub for this course. And you go to, you can easily get here by search GitHub and Vicent-WQ, you're gonna have it. It's pinned there. It's called course EEG. And if you hit the Better button, you're gonna have it run there. So in this course, what I would like to discuss with you is first, how to formulate your clinical questions in a causal way. And second, the basics for causal inference. And the last, how to estimate the causal effect. And I'm gonna give you an example. So if you're doing a search about like causal clinical to say how many papers have been published in regarding clinical applications using causal methods, it's increasing. Causal itself is in clinical research, neurology, psychiatry, and neuroimaging. It's increasing. And also it's, you see the y-axis is in using log scale time-based, which means exponentially. Okay, so let's get a sense of causal language. So in Maria's example, we are looking at the effect of neuro-APO for PD patients, right? So if we're trying to ask a causal question, it can be what the effect will be if the PD patients, maybe with some specific characteristics, take or not take neuro-APO. So from this question, you have a sense that we are trying to do a counterfactual prediction, which is we're trying to predict something that hasn't happened. It's difficult. So why causality is important? I believe everybody here is a researcher, right? So scientific research itself are causal in nature. We're trying to discover the causal mechanism for some sort of like neural functions and etc. And why causal analysis is different from the traditional analysis? That is because we are trying to do a very difficult prediction, which is counterfactual prediction. And it's usually it's formulated like what will happen if we do something or not do something to our subjects. So it's quite related to precision anything, like precision psychiatry, whatever. So, but do remember, in most cases, association does not imply a causation. So a lot of people are talking about causality, and we are confusing. We're confusing because we don't have a formal definition of causality. Some people are saying that causes are the events that produce other events. And some others say causes are the factors that events depend on. And some people are claiming that there's no causation without manipulation. And the question is, are we really able to manipulate everything? I don't think so. So then how to do causal inference, or how to describe causality? The two important things are we need causal assumptions, and also we need a causal model. We need to know what we're doing. So there are 3 steps for doing causal inference. The most important thing is you need to specify your causal model, but this is only for the model-based inference. There's a bunch of research that is for like model-free estimations, and I won't mention that because that's too complex, and you need all the basic information from here. And the second thing is you need to specify your assumptions quite as clear as possible. And the last but very important thing is you need to carry out sensitivity analysis. Sometimes people call this refutation test. It's a test saying if your assumptions are not true, what's going to happen to your estimates, okay? So let's start with some basic notations. Usually we use Z to represent the intervention or exposure or treatment. Usually it's something that you can change to your experimental unit. And the second thing is outcome. which you would like to preserve, or you would like to change based on your treatment. And another thing is observed covariance or confounders, X. What is X? X is something that is behind your treatment and your outcome. Sometimes it can affect both your treatment and your outcomes. We call them like common causes. Also, of course, not a single experiment is ideal. So there may be some very important covariance we're not able to observe. So we call them unobserved covariance. We need to do a refutation test or sensitivity analysis for this guy because this is really very common in practice. And then, if you're doing a search, okay, on causality, usually you're gonna get two results, two branch of research. One is mainly from the statistical world. It's called potential outcome framework, which is proposed by Rubin and these guys. You have the paper there. The other one is a structural causal model, which came from the computer science world. The very famous person, Jodel Pearl, is there. He is a mathematician and a statistician and also a computer scientist. And he has a whole theory for that. And I like to put both of them here because they are really mathematically are connected. There's a paper describing their relationships, and using the graph model to do the illustrations is very nice and easy to understand. You can see that later. So here I put all these concepts here. So let me see. Okay, so you have your individual or unit, which is the unit of the experiment. You have a treatment here. You're gonna give or not give the treatment to your subject. Then here is important. So in the potential outcome framework, for each subject, you're gonna have two potential outcomes. One is this guy takes the treatment. The other is this guy doesn't take the treatment. So the causal effect here is not the difference between two groups. It's a difference between the single subject. The difference between the outcome when this guy takes the treatment and the guy didn't take the treatment, this is the causal effect. So this is called the individual treatment effect. I'm gonna give more mathematical formulation later. So this is the procedure how we usually do our experiments, right? From the population, we just take a small subset in our experiment. Of course, we really want to do RCTs because it gives us reliable information. Then later I'm gonna tell you why RCT gonna give us the most reliable information. So then you split it into your two groups, control group and your special group, right? And then you observe some results and for normal statistical analysis, you're gonna do a group comparison, either like the group test the group means and this sort of thing. But for causal inference, very interesting in the average treatment effect, i.e., for this at least for this sample, what the average effect will be if these subjects take the treatment and minus if they don't take the treatment. So we also have the definition of average treatment effect for the control group and for the treated group. These are different concepts. Okay, so yeah, so as we know, the fundamental problem causal inference, the most difficult part is we're not able to observe the outcome for each unit that both take and not take the treatment because we're only able to observe one of them. Thus, this is a missing data problem. A lot of statisticians are going to be happy because we have so many methods to deal with the missing data problem. Luckily, it works here. Okay. So in order to identify the causal effect, we need to make, from the observational data, we need to make assumptions. So here is a basic assumption for doing causal inference. It's called Schutwa. It's a stable unit treatment value assumption. What is this? So it's assuming that there's no interference between units. We need to think about it because this is really a strong assumption. Why? When people are doing research on social psychology, right? They are studying how people are interacting with each other. So Schutwa here, if you're doing a social psychology experiment, right? It's gonna assume that if one of the subjects receives any treatment, it will not affect other subjects' as outcome. It's a straw because it's saying that your treatment affects only one subject without affecting others, and other people's choices won't affect your choice of taking or not taking the treatment. So this is super strong, and sometimes it's not realistic. You need to really think about it. So second one is simpler. It's no different versions of a treatment, which means okay, if you only have like limited number of possibilities for your treatment. For example, it's the most simple case. It's take the treatment or not, or the dose of some medicine you take. Okay. So what this assumption offers us, it allows us to have the expression of the outcome, like here. So you can write for this case, it's the binary case. Like so, the treatment is have only two options. One, you take the treatment, or you don't take the treatment. So this guy is if you take the treatment, what the outcome will be, and if you don't take the treatment, what the outcome will be. This is the average of them. Okay. So let's go next. After that assumption, we need to specify in our effect of interest. What causal effects are we most interested in? So usually what we do is conditional average treatment effect. Conditional on what? On the confounders and covariates we have there, because we are able to observe them. Or if you go to the population level, you're gonna have like average treatment effect, which is the expectation of the subject who takes the treatment minus the outcome that the subjects don't take the treatment. So you also have ATT, which is average treatment effect for the treated, and also the treatment effect for the control. And also you can, if you can have the ratio effect as well. Like you can use that as well. It's a similar thing as in what you learn in statistics. So when we're talking about potential outcomes, we're actually trying to predict in a hypothetical or maybe a parallel world. We're doing predictions in a parallel world. So here, the important thing is the assignment of the treatment. Why this is important? Because when we are trying to look at the causal relationship between between Z and Y, we need to make sure that there's nothing else which is driving driving Z and Y at the same time. And the randomness is important because if you randomize the treatment, for example, in RCT studies, you will randomize give the treatment randomly, which means you are trying to break the connections between any covariance and treatment. This allows you to interpret the effect between Z and Y, the causal effect, not confounded by anything. So this is why randomness is important. So of course, this is not the only assumption we need to make, especially when we are working on the observational data, which we really don't know the assignment of the treatment mechanism. So okay. then it's the unconfounded assignment. So people are saying, okay, if you're doing causal analysis, will you give me causal effects, or why you're able to magically get the causal effects from your methods? Why? Because this came from one assumption. It's called an unconfoundedness, which states there's no there's no confounders. There's no confounders that we didn't observe. That means we already all the confounders have been observed. They are in X. But actually, in most of the cases, this is not true. That's why it's an assumption. So that means if you don't carry out the RCT, if you don't randomize your assignment of treatment, you're not able to get a real causal effect. You're using these sort of methods. Actually, the only purpose is you're trying to mimic an experiment based on your observations. In that experiment, you're trying to use methods to make the hypothetical experiments looks like it's randomly assigned. So unconfounded assignment is expressed as this equation here. You can see that this is saying that your assignment of treatment based on your covariates and your outcomes equals to the assignment only based on your covariance, not on the outcomes. Which is saying that in your experiment, your assignment of a treatment won't depend on your outcome at all. And if you're looking at this guy here, and if you ever heard about something called a propensity score, this guy is exactly the propensity score. And the propensity score is how likely your subject or unit going to receive the treatment condition on your covariates. That's the propensity score. So one branch of causal research is based on the propensity score. Going to use propensity score to balance, or they can use the propensity score to do a matching, so that all your units there are likely to have the same probability to be selected to either groups. Or you can use inverse propensity score weighting. That's going to give you a causal effect. But this causal means we're creating a hypothetical experiment based on our data, as if all these treatments are assigned randomly. This is not the real causal effect. The only causal effect can be estimated from true randomness of your treatment. So this is the most difficult part. And this is also why RCT is a gold standard for estimating causal effect. And the unconfoundedness assumption, also called ignorable assignment, or ignorability, that's because you're ignoring all the potential confounders. You're saying, okay, they won't affect our results, okay? So here I stress again, so when you're doing randomized controlled experiments, it's okay. You're able to make causal claim based on your data. Even though you're just like comparing two groups, it's okay because randomization has already break the relationship between the anti-confounders and the assignment of your treatment. But in observational studies, you don't know the mechanism of how to assign the treatment, so you need to make additional assumptions if you're doing causal analysis here. Okay. So in general, there are two main overarching methods for estimating the causal effect. One is imputation. We mentioned before. This causal analysis is is equivalent to missing value problem. So you're able to use a missing value method here. And also you can do the weighting. You can do weighting. For example, propensity score is something you can use to do the weighting, like inverse propensity score weighting. And this allows you to make causal claims. And yeah, so of course you can get this information. Use different use different family law methods, like the frequencies prefer to use asymptotic normality, like at some point or at some instance, your estimate gonna have a asymptotic normality, and then you're able to treat everything as normal distribution, and then you have all your normal distribution stuff. And for Bayesian, you're gonna base on your data. You have posterior distributions, and you do a lot of inference. So it's a similar family law. It's different family law methods. So causal inference and the missing data problem have very good correspondence. So when you're running a completely randomized experiment, it's equivalent to a missing completely at random situation. That's one of the assumptions when you are doing missing data imputation. And also, if you're having observational studies with unmeasured confounding, it's missing not at random. Additionally, for this case, you need to make assumptions about the missing mechanism and deal with it somehow. So, okay. And there are other sources of biases when you're trying to estimate the causal effect, right? The selection bias is one of them, and also the measurement bias. Here I would like to stress the measurement bias because for neuroimaging, it's not a direct measure. It's not an ideal measure of the brain, no matter function or structure. So this you need to take into consideration the measurement error. So okay. Now comes to mediation. So what people usually do to estimate the mediation effect? So they're using a structural equation model. They have a model for the direct. Oh, sorry. They're gonna have a model for direct effect. For example, you take this treatment and you're gonna change your outcome. Okay. There's another path that you take the treatment. This treatment gonna change something else, and this gonna change your outcome as well. For example, in the neural EPO example Maria has been working with, qEEG is a mediator here. So taking the treatment neural EPO gonna change your qEEG, and also taking the dose of neural EPO, it's gonna change your cognition directly. And then you have two paths. What people will do is you estimate the direct effect, which is C, and also the indirect, which goes from A to B and then to the outcome. The total effect is going to be C plus A times B. That's the total effect. So here they have the models, and for detailed information, you're going to you can read this paper. Why I mention this? Because mediation analysis is important for a lot of clinical settings and experimental settings. So, what if we use causal inference in mediation analysis? Here we go. So we are going to ask lots of what if questions. So first we have what if here. What the outcome will be if this guy take or not takes the results. Here's a potential outcome, right? For the mediator, you also have the potential, the mediator's potential effect. So if this mediating pathway exists here, and what will be if the qEEG is mediating the dose effect, or what's going to happen if this mediator is not there? So then you need to do a lot more tests, like It's similar, but you just need to test more what's going to happen if this path is not there. And you have lots more like potential outcomes, right? So here, what we use to describe the causal mediation effect, we have average causal mediation effect, which is average with average of all these mediation effects. And we have average direct effect, which is here. It's just like a normal causal, how you estimate the normal causal effect. And also you need to do a bunch of sensitivity or refutation tests, like if the assumption from this pathway are violated, what the results will be, and then for these guys. That's okay. So that's everything about the basics and the theoretical part. Now we move to the practical part. So actually, we have a bunch of tools for doing causal effect estimation. So if you like R more, you have PS weight, which is created by the Fan Li's lab. It's built based on the propensity scores and they can do both weighting and also matching, and then estimate the average treatment effect for you. And also you have mediation and mediation toolbox, which is created by EMI, and it works pretty well as you know. So if you like Python more, which have more powerful machine learning capabilities. So you have DoY, which is created by Microsoft. It's nice. It's open source. You can use that to estimate the causal effect and to do the refutation test later. I'm going to show you. And also economical machine learning. It's a similar thing. Okay. And there are still a lot of tools that are in development. And don't worry, they have MATLAB tools as well, so it's okay. We're fine. So I can take the example of a neural EPO, but in a parallel world, which means I'm doing a simulation of this causal graph, and then show you how we do the causal inference. And you can find the code for this example in the notebooks in my GitHub repo. And here is how we describe graph in Python, right? It's called graph modeling language. This is a very standard description of graph. So first, we're gonna say, okay, we're using a string to describe this graph. First, we're going to say whether this graph is direct or indirected. For causal mechanism, it's always directed because we need to know the mechanism. We need to know who goes to who. And now you need to define your node, right? I have a node ID, which is Z, and its label, its name is neural EPO. Then you define all the node, you define all the edge, and then the graph is here. Okay. So next, you need to define the model. So here you need to tell the model what data they need to use, and what is the treatment, what is the outcome, and potentially what is the common cause. And then you need to input your graph model created just now, and then they're gonna give you a rough estimate. The funny thing is, so DoY gonna remind you that you have some assumptions, it's like this. So it's funny. Okay. Then you can also do the refutation test or the sensitivity analysis. Here you're saying, okay, what's the effect going to be if we have a random common cause, which is not there in your data? This is also a what-if type of a query. And then they're going to do a permutation test and then add a common cause for your treatment and outcome and do a permutation test. So for here, the results is like you have a new effect with a very large p-value, which means after this test, your effect won't change too much, won't significantly different from the one you already estimated. So okay, this is I can put it here and jump to the hands-on session. Okay. Oh, wait a minute. So I can go here. Oh, it's over here. Okay, so Thank you. So if you find this Git repo, you're gonna have all the information here. You will have the slides here, and if you go to notebooks, you're gonna have everything, right? The code is here in Jupyter Notebook. But here, if you hit binder, it's gonna run on server and show you the results. Let me see whether this guy is still here. No, I think this is not working, but don't worry. So if you hit here, this is show, right? Okay, it's creating the running environment for this code. Once it's finished, it's going to be here, and you can play with the code even on your own phone or on your own laptop. Okay, it's coming. So let's go to another example. Okay. Okay, so yeah, here you need to select one of the kernel here, and you can run everything. Yeah, restart kernel and run everything. It's gonna be, you see here, it's running. In this example, we're using we're in a parallel universe of Maria's experiment. Okay, here I write two functions. They're doing something interesting. So first, we need to write using the graph modeling language, right? I'm just using a for loop to put all the node and the link weight in the right place. It's pretty easy. And the other is just like make the visualization a bit better. So now comes to our model. So we see here in Maria's experiment, the experiment setting is like this, but here we would like to change something. So, okay, so here we are writing this is a model for the mediating effect, right? Okay, I have comment here. So this is for the mediating effect, which comes from this is the treatment, I think. This is treatment. This is a mediator, and you have in your outcome you have the effect both from the mediator and directly from the treatment. So what we are going to do is trying to estimate these coefficients, these effects from randomly generated data based on this model specified. So okay, here we have a function to generate the data. They are all fake. Okay, we have the observations. I show five of them for you. They have the observation of neural APO, qEEG, cognition, and education. And then this is a new model we specified, which is different from Maria experiment. So we have a neural APO, right? Direct effect to cognition and indirect effect from via qEEG to cognition. And here we have a common cause of education. What's this? So sometimes people with higher education are easier to accept like new technologies or new treatment because neural EPO is not a very well-known or a medicine that has been used a lot. It's a new medicine. People need to test the effect. Okay. We have a common cause here. And then I leave a error intentionally here. So I'm writing this because when you are using the default viewer from their tool, they only give you the skeleton of your graph. They don't give you the weight. And here, if you change this guy, actually this is the layout of the graph. If you are using a new layout, problem will be solved. Okay. You comment this. You go here and you go run everything now. Else. No, problem solved. Okay. Now you have the weight on your link, so you can make your graph looks super nice by like tweaking these parameters. And then after that, we're we are choosing our estimate, but now I'm using default setting because we're using we are generating everything from normal distribution, so the default setting can be okay. And then once you specify the estimate, the effect of interest, you're gonna estimate that. To estimate the effect, you need to specify the methods you use for estimation. Okay. Oh, sorry. I think I skipped this one. You need to specify everything so that they can. Okay. After they finish, it's gonna give you a. Oh, sorry. This is refutation test. So here, the treatment, if the average treatment effect they obtain is 0.3. So is that correct? Is the total effect of neural EPO to cognition is 0.3? Okay, so they have a direct effect here is 0.9, right? You have an indirect effect via qEEG, right? But here I put minus 0.6. You see this. If you tie 1 times minus 6 and then add 0.9, it is roughly 0.3, right? Okay. Now you see that it works. Okay. You can change the model here, right? If you're interested, you can change the parameter here to say whether it works well. It's pretty fun. Okay. Now let's go to sensitivity analysis. So the first thing is, let's say what will the effect be if we add a common cause. So after some computations, they tell us it's not significant, which means adding common cause won't change now the causal effect here, which is pretty okay, right? Our causal effect is robust by now. And then let's do another test. So what the effect will be if we replace the treatment with a placebo? And then with some computations, this is just to forget about the warnings. So it gives you very results. Why? Because I think there's some numerical problems here. So for this test, we're gonna ignore that because there's numerical errors here. If we want to do it, we need to look into this tool and to see what's gonna happen. I think I forget the second test. The second test is what will the effect be if we no. Oh, okay. Sorry, it's this guy here. So what the effect will be if we only have less data? For example, we only have 40% of data. It's still robust, right? We don't need that much data to estimate this effect. So if, let's say, what's going to happen if we have less data, even less, let's say 1%. It's going to take some time. Then it's still robust. Why? Because we're creating the very ideal observations from normal distribution, which means it's robust to lots of this sensitivity analysis. Okay, after that, there's a very simple example for doing this is a mediation analysis, right? I put again this mediation graph, and using stats models is very similar to use the toolboxes in R. You're writing your outcome model using the formula like this, right? The cognition going to depend on neural EPO, this is a treatment, and the qEEG, this is a mediator, and education, which is a common cause. And for the mediator model, it's gonna receive the effect from treatment, which is neural EPO. And then it's gonna take some time to estimate, and after that, they're gonna tell you all the important results of a causal mediation analysis. That's example. You can just try to play with it. Okay, here it is. So you have the average causal mediation effect for the control, which is minus 0.59 something. It's very close to the minus 0.6. So apparently I think we're doing the estimation doing a good job. So the total effect is still like 0.3 something. right? Everything is very significant. You have the I think this is the proportion mediated, and also this is the average mediation effect, and this is average direct effect, and this is everything. So yeah, this is example. That's the end of practical session. I think I'm gonna go back to. Do I have time? Yeah, it's more or less okay. So the take-home message. So most scientific research are causal in nature. Thus, causal reasoning is inevitable, I believe. So, and also EEG and qEEG are very important because, and of course, they are not ideal observations. So when you're using the EEG and qEEG measures, we know that it's only a reflection of brain functioning, and their roles in clinical neuroscience still need our research to validate. Okay, it's nice. It's nice tools. And we have tools and software for causal inference there. It's there. No matter you're using R or MATLAB or Python. I put Python R here. It's because I'm more familiar with that. I'm sure there are MATLAB-based tools there. And also open access data pipelines and platforms like CBrain allows us to improve the research, the generalizability and interpretability of our research. And if you like that, I can make all the causal analysis plugin in CBrain so that you can just grab the results from qEEG and do your analysis. Of course, you need to specify your causal model and causal assumptions. And okay, so there's a homework. They told me this is a course. so in Maria's paper, they're sharing their data, right? You have the data there. You can try to use causal model to see the causal effect of neural EPU there, right? It's gonna be interesting. Okay, the data is already there on Open Neural, and I think you can use the data maybe on CBrain directly. So, yeah, some other interesting stuff. If you're interested in a theoretical background of causal inference, find these courses is pretty nice. I love that a lot. And also, if you want more knowledge on the data science, like statistics, machine learning, and how to use these computer science tools to improve your research. The course is here. It's McGill's qualitative life science course. Pretty nice. And also there's another book here. It gives you a lot of like practical help, how to use these toolboxes and these sort of things. Okay, so enjoy the course and the annual meeting. Thank you.